let's talk about a huge shift in how we build things. I mean, the really complex stuff. Think airplanes, think massive structures. The old way of doing things, with these rigid, fixed assembly lines, it's on its way out. We're stepping into a new world of smart, flexible manufacturing. Let's dive in. So here's a question that keeps engineers up at night. You can spend months, even years, perfecting a digital design, right? A flawless blueprint on your computer. But the second you try to make that thing in the real world, suddenly it's not so perfect anymore. Tiny little flaws just appear. So how in the world do you build something like a perfect airplane when all your pieces are just a little bit off? And believe me, nowhere are the stakes higher for this problem than in aerospace. We're talking about these massive, incredibly complex fuselages. They're built from these really cool, advanced materials like carbon fiber reinforced polymers. You'll hear it called CFRP. Now, this stuff is amazing. It's super strong, super light. But it has this one little quirk. It tends to warp and deform just a tiny bit when it's being made. And that quirk, right there, leads us to the heart of the whole problem. It's this idea of as designed versus as built. Think of it like this. As designed is the perfect plan on your screen. As built is what you're actually holding in your hand from the factory. And they are never exactly the same. We're talking tiny, tiny differences, but when you're trying to join two massive pieces of an airplane together with perfect precision, those tiny gaps become a massive headache. So, how have we been dealing with this headache? Well, for decades, the answer has been pretty clunky. It's basically a super expensive, super frustrating cycle of just fixing stuff over and over. Okay, take a look at this flowchart. This is the old way, and it's painful. You bring in your component, you try to fit it into place, and you measure it. But what happens when it doesn't fit perfectly? And spoiler alert, it almost never does on the first try. Well, you fall into what's called the rework loop. It's basically a manufacturing hamster wheel of trying, failing, and trying again. And this cycle is just as bad as it sounds. If the part doesn't fit, you have to take the whole thing apart again. Then comes this process called shimming, which is a fancy word for manually sticking tiny little fillers into the gaps to make it fit. Then you put it all back together, measure again, and hope for the best. You just keep doing this over and over until it works. It's slow, it's all done by hand, and it's just a massive waste of time and money. And here's the real kicker. All that time, all that manual labor spent on shimming, it adds a ton of cost and risk to the project, but it adds absolutely zero value to the plane itself. Think about that. You're pouring money down the drain just to fix a mistake, not to actually improve the product you're building. But what if there was a way to just skip that entire rework loop, to break the cycle completely? Well, there is. And it's a whole new way of thinking called Assembly 4.0. This really breaks it down. The old way was make and fix. You build it, it's wrong, you fix it. The new way, measure and adapt. Instead of manual shimming, we're talking about elastic correction. We'll get to that. Instead of giant fixed machines bolted to the floor, we're talking mobile robots. It's a complete flip. We're going from reacting to problems to proactively managing the shape of the part before it even becomes a problem. And this is the genius idea at the center of it all. Remember how we said those CFRP parts can deform a little? They're slightly flexible. So the new thinking is, why try to permanently fix the part with shims? What if instead we could just temporarily make it perfect? Just for a moment. We can actually use that flexibility, gently bending and coaxing the part into its perfect, digitally designed shape right at the moment of assembly. Okay, so how do you actually do that? Well, you need a special kind of tool. You need a robot that's more than just a dumb gripper. You need a robot that can actually reshape things live, in real time. And here it is. This is the heart of the whole system. It's called a form-flexible mounting frame. It might look kind of complicated, but the idea is actually pretty simple. You've got lightweight carbon fiber tubes for the structure. You've got vacuum grippers that hold onto the part without scratching it. And then you have the linear actuators. These are the muscles of the operation. They're what do the actual pushing and pulling. So let's put it all together. Those carbon fiber tubes, they're telescopic, so the frame can adjust to different sized parts. Super flexible. The vacuum grippers latch on tight, but they're gentle, so they don't damage anything. And then the most important part, those actuators. They are like a whole bunch of incredibly precise robotic fingers all working together to gently squeeze and stretch the component back into its perfect original design shape. But wait, How does the robot know exactly where to push and pull? It needs eyes, right? Well, it has them. This incredible 3D scanning system projects these fringe patterns of light all over the part. This creates a perfect digital map of the surface, showing every single tiny imperfection down to a fraction of a millimeter. And all that data gets fed back to the robot's muscles, the actuators, instantly. And now for the full picture. You take that amazing shape-shifting frame and you stick it on the end of a mobile robot. Now we're really talking. You suddenly have a system that isn't chained to one spot on the factory floor. It can literally drive over, pick up a huge aircraft part from a storage rack, and get this, it starts correcting the part's shape while it's driving across the factory. Then it delivers it to exactly where it needs to go, holding it in that perfect shape for assembly. It's not just a gripper. It's a gripper, a shaper, and a delivery truck all rolled into one smart mobile unit. It's incredible. So what's the big deal? Why does this matter so much? Well, honestly, this changes pretty much everything about how we think of a factory. First off, that horrible, costly rework loop, gone, just completely eliminated. That means assembly is way faster, way more efficient. But the really huge change is the factory itself. You're not stuck with a rigid, straight assembly line anymore. Imagine a factory floor that's more like an open dance floor, with these mobile robots moving around, working together in flexible little groups. It frees you up to build bigger and more complex things than ever before. And this brings us one giant step closer to a concept you're going to hear a lot more about, the digital twin. The dream is to have a perfect real-time digital copy of everything happening in the physical world. This system does exactly that for assembly. By constantly scanning the real part and forcing it to match the digital plan, it closes that gap. It makes sure that what you see on the screen is exactly what's happening on the factory floor right now. So it really leaves you with a pretty wild thought, doesn't it? What does a factory even look like when you don't need fixed assembly lines anymore? When the whole process is just a flexible, dynamic dance of smart robots? It changes everything, from how we design products to how we run our supply chains. The future of making things is going to look very, very different.